In earlier tapes in this series, we have frequently referred to the vital importance of correct relay operation in order to maintain system stability. In this tape, we're going to take a closer look at the subject of system stability, and then go on to examine the role which protection schemes play in this. But first, what exactly do we mean by a stable or unstable system? Well, in simple terms, we refer to the power system as being stable when A, the power demands and losses on the system are being adequately supplied by the power being generated. This may include some power being imported from a neighboring utility. B, the frequency is stable and close to its nominal value. This is because power supply and power consumption are equal. C, the voltage is close to its nominal value at all points in the system. D, all of the transmission lines, transformers, generators, and other equipment are working within their rated capacity. Unfortunately, this perfect, steady-state condition rarely lasts for more than a few seconds because the customer load demand is always changing. But these changes in load are relatively small, and moreover, they are usually anticipated according to the time of day and weather conditions. As a result, there is normally sufficient generating capacity online, and with the help of automatic equipment such as turbine governors and voltage regulators, the power supply can be quickly adjusted to meet the load demand. Adjustment of the turbine governor's set point regulates the mechanical energy input to the generator and consequently determines the electrical output. This situation is the same whether the generator is driven by a steam turbine, gas turbine, or a water turbine. It may take several seconds for governor adjustment to achieve the required change in generation, but this is quite adequate for normal minute-to-minute variations in load demand on the system. Similarly, the voltage regulators are relatively slow to adjust the excitation of the generators and so meet the change in demand for reactive power. So even in this steady state, stable condition, slight changes are always occurring to the flow of real and reactive power along the transmission lines. Consequently, the load angle or power angle is also changing continuously. Now, what is this power angle? Well, in order to transmit power across a transmission line, in this example from bus 1 to bus 2, there must be a phase angle difference between the voltages V1 and V2 at each end. This is due to the inductive reactance XL of the transmission line. The resistance of the conductors is relatively small and is usually neglected in these studies. Let's look at a simple example of a single generator feeding a load through a single transmission line. If we consider the load demand at bus 2 to be at unity power factor, then the current is in phase with V2 as shown here. As this current flows through the transmission line, the inductive reactance produces a voltage drop, IXL, which is 90 degrees out of phase. As a result, the V2 voltage will lag with respect to V1. If the load demand at bus 2 increases, there will be an increase in current flow, so the voltage drop, IXL, increases like this. Consequently, the receiving end voltage, V2, lags further behind V1. The power angle, phi, increases as load increases. The value of the voltage drop, IXL, is approximately equal to V1 sine phi. Dividing this by XL, we can find the current. I equals V1 sine phi divided by XL. As power received is proportional to V2I, the amount of active power transferred along the transmission line is proportional to V1 times V2 sine phi divided by XL. Now, let's look at the situation from the point of view of the sending end, that is, this generator, or perhaps several generators feeding the same bus. Normally, the generator is feeding into a very large power system. In order to transfer active power along the line, the voltage at this sending end must be leading that at the receiving end. This is in accordance with our power angle equation. In order to transfer more load along the line, the power angle must be increased by advancing the sending end voltage. This is achieved by increasing the energy input to the rotor. Studying the power angle equation, we can draw several important conclusions. The amount of power that can be transferred along a line can be increased by increasing the voltage. Of course, increasing the voltage implies that the transmission line hardware, insulators, and so on must be upgraded. But it does show one of the reasons why high voltage and extra high voltage is favored for transmission. It also shows why it's important that voltage levels must not be allowed to fall during operation. Another clear factor is the line inductive reactance. By reducing XL, we can increase the power capability of the line. An obvious example of this is when two lines run in parallel between two buses, so reducing the total impedance by half. This allows us to double the capacity of the circuit. But let's look at this other factor again, the power angle phi. This curve shows the transfer capability of the transmission line with relation to the power angle between the voltages at each end. When there is no angular displacement across the line, there will be no power flow. As the power angle increases, so does the load transfer. For example, where the angular displacement between the voltages is 30 degrees, then the power transfer across the line is equal to the sine of 30 degrees, that is 0.5 or 50%. At 90 degrees, the sine of the angle is equal to 1, so the load transfer is now maximum. If the angle increases beyond 90 degrees, then the load transfer begins to fall again because the sine of the angle diminishes. So here is an important conclusion. In order to increase the transfer of power across a transmission line, the power angle must be increased up to a limit of 90 degrees. If the power angle exceeds 90 degrees, then the power transfer will be reduced, and the system will probably fall out of synchronism. For stable operation, the system operator loads the system in such a manner that the load angle across each transmission line is much lower than 90 degrees. Let's look at a simple example. Here, the line is operating at approximately 40% capacity. The load angle across the line is about 25 degrees. In order to increase the load transfer, the operator must first increase the steam input to the turbine by adjusting the governor set point. This causes the rotor to accelerate and so advance the angle of voltage, V1. This now increases the power angle across the line and so increases the load transfer. After a brief oscillation, the governor settles down to its new position with the power angle now at, say, 45 degrees. What would be the situation if we had two identical transmission lines connected between the same buses instead of one? Now, the reactance between each end of the line is divided by 2, and therefore the transfer capability has been doubled for each particular angle of displacement. A new power angle curve can be drawn to represent this condition. On the curve, we can see that for every power transfer angle, the transfer capability has been doubled. For any particular value of load transfer, the load angle required is much less. Also, for any change in load, the required change in power angle is also much smaller. This means that with two lines in service, the operating point is a long way from the 90-degree limit of stability. It is apparent that this connection is more able to withstand fluctuations and remain stable than the single line connection. And for this reason, care must be taken when removing a line from service. In this example, we have generation and load at each end of the transmission circuit. At bus 1, the generation is 8,000 megawatts, while the load is 7,200 megawatts. The remaining 800 megawatts flow across the connection, that is, 400 megawatts in each line, and this supplies the load at bus 2. 2,000 megawatts are supplied from the generator at bus 2 to feed a load of 2,800 megawatts. This curve shows the situation with the two lines in service. In order to transfer the 800 megawatts across the transmission circuit, the voltage at bus 1 must be approximately 25 degrees ahead of the voltage at bus 2. If one of the lines is switched out of service for maintenance, all of the 800 megawatts will flow across a single line. In order to maintain this same load transfer, the generators feeding bus 1 must advance in phase so that the voltage at bus 1 is now about 60 degrees ahead of the voltage at bus 2. With this large angular displacement, we are already approaching the stability limit of the line. In order to avoid this, the system operator would probably reduce the load transfer before switching the line out of service. But this may not be possible due to the loading around the system. Now, in this precarious situation, any disturbance on the power system, say a loss of load or a loss of power generation, may cause the voltage at V1 to advance further, or perhaps the voltage at V2 to lag such that the load angle between them exceeds 90 degrees. Beyond this point, the load transfer across the line actually decreases, so the generators at bus 1 accelerate in an attempt to increase the load transfer. This in turn increases their angle of lead even farther, so that the power transfer continues to decrease. At this point, the generator rotors are advancing on those at bus 2. When the rotor passes the 180-degree mark, it's now approaching V2 again, so it can be considered to be lagging. It is trying to catch up to V2. But look what's happening to the power curve. Once the voltage displacement falls beyond 180 degrees, the power flow along the line reverses. Bus 2 is now feeding bus 1. The power flow in this direction is trying to assist the generator rotor at bus 1 to catch up. This is instability. The reversal of power flow in this line will probably create large disturbances on other parts of the system. Hopefully, the generators at bus 1 will pull into phase and remain in phase as they recover their original position. However, experience tells us that this is not likely to happen, and the generator will probably continue to accelerate and remain out of step with the system. This condition is known as slipping a pole and is the symptom of instability. The only remedy is to disconnect the unit from the system and then resynchronize. At this point, let's take a break, and then we'll come back and look at other factors which affect stability. For now, please switch off the tape and review this material in your workbook. In the previous segment, we saw that the voltage phase displacement between the two ends of a transmission line determines the amount of load transfer that can take place. Actually, the phase angle of the voltage at the sending end bus is determined by the physical angular position of the generator rotor, which is being driven by the prime mover, say a steam turbine. As the rotor accelerates and moves ahead, so does the corresponding voltage, which is generated in the stator windings. There is actually a small angular displacement between this voltage and that of the bus due to the reactance of the generator windings themselves. Moreover, a transformer is often connected between the two, so adding more reactance. However, this is usually small in comparison with the reactance of the transmission line. When electrical load is applied to the generator, more current is drawn, consequently increasing the magnitude of current flowing through the stator windings. This current creates a flux which tends to act as a brake on the turning action of the rotor. In order to maintain the machine's speed and restore frequency, more steam must be supplied to the turbine in order to increase the mechanical output. All of the mechanical energy of the steam is transferred along the turbine shaft into the generator rotor. From here, it passes across the air gap in the form of magnetic flux into the stator, where it is converted into electrical energy. In order to maintain a constant speed, the mechanical energy input must precisely match the electrical load output. As load demand changes, the turbine governor will continuously adjust the steam input so as to produce the required mechanical input. However, as we mentioned in the last segment, this action may take several seconds to complete. The governor is far too slow to account for system disturbances. For example, in the case of an electrical fault or perhaps a load rejection, the output from the generator will fall drastically, and it will fall immediately. At this instance, then, the turbine is continuing to supply mechanical power. In this situation, the turbine's speed will begin to increase and so advance the generator rotor. This short period of time during imbalance, immediately following the disturbance and before a new steady-state condition is arrived at, is known as the dynamic period. The dynamic response during the first half second generally determines if the system will remain stable or not. You can see now why high-speed protection and removal of faults from the system is highly desirable. Let's look at a few examples. Here we see a single generating station supplying 1,500 megawatts across 3 transmission lines into a very large system. The generation on the large system is 50,000 megawatts, so the total load is 51,500 megawatts. Each of the transmission lines is carrying 500 megawatts. The power angle between the two buses is shown by this curve. With 3 lines in service and a total load transfer of 1,500 megawatts, the load angle here is about 30 degrees. You can see that with 3 lines in service, we could actually transfer more power. At a power angle of 90 degrees, the capacity of the transmission circuit is about 3,000 megawatts. This curve does not show speed or frequency, although it is a sine wave. It indicates the phase angle difference between the 2 voltages at each end of the line and the corresponding quantity of power which is being transferred. This vertical axis shows the megawatt output of the generator, and this is, of course, the same as the mechanical input from the turbine, ignoring the exceedingly small losses. Turbine input is considered constant for the very short time periods shown. Now, a disturbance causes one of the transmission lines to trip out. The total impedance of the transmission circuit has increased. Therefore, at this instant, the power transfer across the line decreases like this. Remember the equation for power transfer, V1 times V2 times the sine of the power angle divided by reactance. If the reactance increases, the power transfer must decrease. But this reduction in load is only momentary. Remember, the turbine is still providing 1,500 megawatts of energy to the generator. As a consequence, the rotor starts to accelerate and move ahead in phase angle. As it does this, the amount of power being transferred across the line is increased once again until it reaches 1,500 megawatts. Once again, we are satisfying the power equation. Although the reactance of the line has increased, the phase angle has also increased to about 48 degrees. So at this point, we should have equilibrium. But it's not so easy, as we have to contend with the spinning energy of the heavy rotor. The acceleration does not suddenly cease at this point. In fact, the rotor overshoots and continues advancing in phase, so further increasing the amount of power being transferred across the line. However, now we have the situation where the generator output is greater than the mechanical input. So the rotor starts to decelerate and fall back to the equilibrium point. After a few oscillations, the rotor will settle again at equilibrium. If we examine the diagram carefully, we find that this overshoot area above the line is of the same dimension as this area below the line. This lower area represents the energy stored in the rotor, which provides the accelerating force. Conversely, this area above the line represents the energy removed from the rotor as it overshoots, and so provides the decelerating force. As long as these areas are equal, the system will remain stable and ride through the disturbance, in this case, the loss of one transmission line. During the dynamic period, the system has quickly settled into a new steady state, with the generator advancing in angle in order to continue to transfer 1,500 megawatts along the two transmission lines. Now let's look at another example on the same section of the power system. This time, the load transfer has been increased from 1,500 megawatts to 1,800 megawatts. Now let's return to our load transfer curves. We can see that with 3 lines in service, the phase angle difference must be increased to about 37 degrees in order to transfer 1,800 megawatts. Once again, consider the case where a system disturbance causes one of the lines to trip. As before, the instantaneous response is for the amount of power transfer to reduce and the rotor to accelerate from this point to the equilibrium condition again, which is now about 65 degrees. As before, the rotor continues accelerating and overshoots and continues to increase the phase angle beyond 90 degrees. At this point, about 115 degrees, the load transfer is once again 1,800 megawatts. But look, this deceleration area above the line is less than the acceleration area below the line. So the rotor goes right on advancing and increasing the phase angle. The power transfer has decreased, but the turbine is still inputting 1,800 megawatts of energy, so the rotor continues to accelerate. Thus, the phase angle continues to increase, and the generator will fall out of synchronism with the rest of the system. We'll be looking at this condition in more detail later on in this tape. From these two examples, you can see that the stability of the system is very much influenced by the initial operating condition. That is, before the disturbance occurred. Okay, let's move along to look at yet another example on the same section of power system. With 3 lines in service, the power transfer is 1,500 megawatts, and from the curve we can see that the power angle is about 30 degrees. This is the load condition that we discussed in our first example. Now let's see what happens when a phase-to-phase fault occurs on one of the transmission lines. In this study, we are concerned with what happens in the very short time frame before the protection relays trip out the faulty line. As we know, a phase-to-phase fault will cause the voltage to fall to a very low level at the location of the fault. This will cause voltages in the vicinity of the fault to fall. Now remember the power angle equation, V1 times V2 times the sine of the power angle divided by reactance, XL. If the level of voltage falls, then the capability for load transfer is also reduced for each specific angle. So we can draw yet a third load transfer curve for the phase-to-phase fault condition. Clearly, with these low voltages for any specific angle, the amount of power that can be transferred is now greatly reduced. We now have to consider three power angle curves. They are: 1, the initial condition with 3 lines in service; 2, the condition with the phase-to-phase fault on; and 3, the condition with only 2 lines in service after the faulty line has tripped. At the moment the fault occurs, the power output falls drastically to this point on the fault curve. At this point, the generator output is far lower than the turbine input, so that there is a large amount of accelerating force available. As long as the fault remains on, this particular curve indicates the condition. As the rotor accelerates and its angle advances, the power input increases along this curve until at this point, say 45 degrees, the faulty line is tripped out of service by its protective relays. Conditions are now indicated by this 2-transmission line curve. The rotor now continues to accelerate along this curve through the equilibrium point and overshoots and starts to decelerate as the generator output is greater than the turbine input. The rotor angle will continue advancing until this decelerating area above the line is equal to the accelerating area below the line. At this point, power output will fall back and after a few oscillations will settle to its new equilibrium position, that is, with a transfer angle of about 50 degrees. This is an interesting case. We can see that the rotor has advanced beyond the 90-degree phase angle. Nevertheless, it's been able to recover and remain in step with the system. Now let's see what would occur if the fault were a 3-phase fault instead of phase-to-phase. With a solid 3-phase fault, the voltage falls close to 0, and the immediate consequence is for the power transfer to fall close to 0 also. As before, the rotor angle advances until the faulty line is tripped at this point, so that load transfer conditions are now indicated by this 2-line curve. Clearly, this accelerating area is greater than before, and as a result, the rotor will advance to a much greater angle. Once again, we must carefully measure and compare these two areas. They appear to be equal. The limiting factor is this point here. As long as this decelerating area above the line is equal to or greater than the accelerating area below, then stability will be restored. However, this condition is extremely vulnerable. For example, if the protection relays operated slower than intended, then the accelerating area would be greater and the rotor would advance beyond this point and fall out of step with the rest of the system. It is clear that a 3-phase fault is more severe and more likely to cause instability than the phase-to-phase fault. It is also apparent that the time settings of all relays are most critical in helping to avoid instability. In these examples, we have been looking at stability behavior on a fairly simple system. Obviously, in practice, it is much more complex. In response to a fault, several generators may be accelerating or decelerating at the same time, and load transfer may be affected on other transmission lines throughout the system. Detailed system stability studies are normally carried out by the utilities engineering department in order to predict the consequences of different types and locations of faults. These studies play an important part in power system design and operation. Obviously, protection schemes are a vital part of system stability. We'll be talking more about this in the next segment. For now, please switch off the tape and thoroughly review this material in your workbook. In the last segment, we noted that system stability can be improved by rapid clearance of faults. When the faulty section of line is removed at high speed, there is less likelihood of the generator swinging out of step and losing synchronism. However, when a line is tripped, the system is operating in a weakened condition, and instability may still occur. One way around this problem is to bring the line back into service again as quickly as possible by automatic reclosing of the breakers. This action is based on the fact that most faults on overhead lines are temporary faults caused by a lightning strike or high winds or other climatic conditions. We have already discussed this in earlier tapes. When the breakers are reclosed after, say, half a second, in most cases, the temporary fault will no longer exist. Automatic reclosing is not usually employed on underground cable systems, as these are not susceptible to temporary faults. A fault on a cable system is usually due to a permanent fault in the cable itself. The type of reclosing scheme employed varies according to the function of the line itself. For example, is it a transmission line or a distribution line? Is it close or far away from a generating source? The reclosing relay generally allows for several attempts at reclosure with different time delay settings. On high voltage transmission and sub-transmission lines, we usually want the line to reclose as quickly as possible so as to help maintain stability. This is usually carried out by the instantaneous setting on the reclosing relay. However, a small time delay of about half a second, that is 30 cycles, must be allowed before reclosure so as to permit the arc to extinguish at the fault. At high voltage, say 345 kV, it takes about 21 cycles for the air gap at the fault to deionize. If we reclose the breaker too soon, the fault arc would immediately restrike. To prevent this occurrence, a time delay between opening and closing is usually built into the breaker by the manufacturer. The actual time will depend upon the nominal breaker voltage. In addition to this, a minimum time delay, say 5 cycles, may be added to the instantaneous relay operation. So the total time delay for reclosure may be about 35 cycles. If the fault is still on the line after reclosure, the protection will trip the breaker once again. The recloser may now make a second attempt to reclose after a time delay of, say, 5 seconds. Usually, these relays allow up to 3 or 4 attempts at reclosing. If the fault still remains on after the final attempt, the reclosing relay locks out and the breakers remain open in the tripped position. The reclosing relay will only reset after the breaker has been closed manually or by the SCADA system to restore the line to service with the fault removed, of course. When automatic reclosing takes place, it is essential that both ends of the line remain in synchronism, or at least close to synchronism. This may not be the case, for example, with an interconnecting line between two power systems. If there is a large power flow over the interconnection before tripping occurs, it's likely that the two systems will rapidly move out of synchronism when separated. One system may speed up, while the other decreases its frequency. The phase angle between the two systems will increase rapidly, and they will not remain in synchronism. In this case, automatic reclosure cannot be used. However, in most power systems, there are many transmission lines operating in parallel. Hence, loss of a line will cause the load to transfer to others. In this situation, the two ends of the line will remain in synchronism, but there may well be an increase in phase angle between the voltages at each end. We have already seen the reason for this in earlier segments of this tape. Indeed, this is one reason why reclosure should be as rapid as possible. Incidentally, in order to obtain high-speed reclosing, it is essential that the temporary fault is cleared by high-speed simultaneous tripping at both ends of the line. This means pilot protection must be used. In this case, high-speed reclosing will be virtually simultaneous at both ends. But remember, if it's necessary to take the pilot protection out of service, it's also necessary to block the high-speed reclosing action. We may run into phase angle problems where the first reclosing attempt fails and the line trips again. The relay then attempts a second reclosure with time delay. In this situation, the phase angle between voltages at either end of the line may be quite wide, and reclosure at this point could cause a shock to the system. How can we get around this? Well, one method is to apply only single-pole tripping and reclosing. Experience shows us that most temporary faults occur on one conductor only, giving us a single phase-to-ground fault. For this reason, many installations choose to trip the faulted phase only. The pilot protection is set up to trip both ends of the line, but on the faulty phase only. For the brief interval of time that this phase is out of service, the remaining two phases will continue to transfer power and so retain synchronism and keep the phase angle difference within a narrow band. The instantaneous reclosing relay will quickly close the breakers again and restore the line to service. Of course, the same protection is set up so that a three-phase fault will trip all three phases at both ends. If single-pole tripping and reclosure is not installed, then another method is to use a synchro-check relay to measure the phase angle difference. In this arrangement, reclosure takes place first at one end of the line only, while the synchro-check is performed at the other end. This relay measures the phase angle of the voltages on either side of the breaker, and it will only allow reclosure if this angle is within a specified limit, say up to 40 or 60 degrees out on the system. Yet another way around this problem of reclosing into a large phase angle difference is to eliminate the second and subsequent reclosing attempts altogether. I am sure that you will find on your system many transmission lines which have reclosing relays, but some of these are limited to only one instantaneous attempt at reclosing. If the breaker trips again, the relay locks out. There are even limitations to the application of the instantaneous reclosing arrangement. This is where the transmission line is located close to one or more large generators. The shock to the generator of suddenly rejecting load, then applying load again, could conceivably cause mechanical stress and ultimate damage to the turbine and generator rotors. For these reasons, and to preserve system stability, instantaneous reclosing relays are usually not installed at locations close to a generator. We can see that the application of reclosing relays depends upon the system location and the specific system. We have mentioned in earlier tapes that when reactors are installed, they are usually connected directly to the transmission line. In this case, automatic reclosing should not be applied. This is because a fault in the reactor is more likely to be permanent than temporary, and we certainly do not wish to reclose and re-energize into the internal fault of the reactor. The same thing goes where a transformer may be directly connected to the line. For distribution feeders, the breaker in the substation is often fitted with a reclosing relay. The first reclosure may be instantaneous, but the second, third, and fourth will each have a time delay of 10 to 20 seconds. In setting the reclosing relay, it's necessary to know the types of load which are supplied by the particular feeder. For example, the feeder may supply an industrial load which includes large induction motors. Reclosure must be delayed until the motors have time to run down and reduce their residual voltage to less than 1/3 of rated. With synchronous motors, it's preferable to trip the motor before restoring the voltage to the line. You'll remember we discussed this matter in an earlier tape. Loss of voltage relays should be installed on all large motors. An even more difficult situation arises where the industrial consumer also generates all or some of his power requirements, and these generators are synchronized into the power system. In this situation, reclosure of the feeder would not be practical, as the two systems would now be out of synchronism, and some damage may occur to the customer's machines. The customer's generator should be tripped before any reclosing takes place on the feeder breaker. On most feeders, there are a large number of fused taps supplying different customers. The protection scheme may be coordinated so that if a temporary fault occurs downstream of any fuse, the feeder breaker protection will operate first. It will instantaneously trip the breaker and then instantaneously reclose again. If the fault remains on, that is a permanent fault, the breaker will not trip the second time, as the instantaneous protection is now blocked. The second attempt at reclosing is delayed sufficiently for the local fuse to operate and clear the permanent fault. Again, you'll remember we discussed this when we looked at coordination in an earlier tape. On distribution systems, another more direct reclosing arrangement is often used in addition to the reclosing relays that we've been talking about. The device in question is known as a recloser, and it is usually installed in the line itself at some remote distance from the feeder breaker. Several reclosers may be installed, particularly at points where different sections are tapped off. The recloser is essentially a switch with limited capacity for interrupting fault currents. This is acceptable because very high levels of fault current occur closer to the feeder breaker, which has greater interrupting capacity. However, further down the line, fault currents are less, and the local recloser will clear that section of line and then attempt to reclose. The operation of the recloser is mechanical, and usually up to 4 attempts are provided with time delay settings between each attempt. Again, all of the settings need to be coordinated with other protection devices on the feeder, particularly the feeder breaker. Actually, the operation of reclosers on the distribution system does not really affect the stability of the power system very much. They are installed with the objective of reducing outage time to the customers. However, on transmission and sub-transmission systems, it's clear that reclosing schemes can help retain stability of the system and reduce the likelihood of generators or parts of the system falling out of step. But unfortunately, instability can and occasionally does occur. In the next segment, we'll be looking at protective schemes to assist the system in such instances. For now, switch off the tape and thoroughly review this material in your workbook. Let's look once again at what happens to a generator when it falls out of step with the system. As the result of a disturbance, perhaps a fault within the system itself, power flow along the line is momentarily reduced. The rotor consequently starts to accelerate. The phase angle increases between the generator rotor and that of the receiving end of the line. As the rotor continues to advance beyond 90 degrees, the amount of power being transferred along the line decreases until at this point the rotor is leading by 180 degrees and there is zero power transfer. As the advance continues, power begins to flow in the other direction, that is, into the generator from the system. The generator rotor has advanced so far that it's now coming around again and is beginning to catch up with the system. It then reduces to zero as the angles coincide. At this instance, the voltages at each end of the line are in phase, and load transfer is zero. All this has happened in about half a second. The turbine governor has hardly had time to act yet, so the generator rotor continues to accelerate. Looking at a specific case, this transmission line has the sending end voltage fixed, with the receiving end voltage allowed to rotate. VR is equal to Vs. Under an out-of-step condition, the locus of VR is a circle. Let's look at the voltage level along the transmission line, where the sending end voltage and the receiving end voltage are both in phase, that is, with no power transfer. The voltage all the way along the line will be approximately the same. However, if the receiving end voltage advances to 180 degrees, the voltage profile along the line looks like this. At the electrical center of the line, the voltage is 0. As the rotor angle changes, so does the voltage profile and the point of 0 voltage. Now to plot current flow during the out-of-step condition. VR and Vs are in phase at 0 degrees, and no current flows as the voltages cancel. When VR is at 90 degrees, it adds to Vs vectorially, giving this current flow. When VR is 180 degrees, out of phase with Vs, the two voltages add directly, giving maximum current flow. When VR is at 270 degrees, it adds vectorially to Vs, giving this current flow. You can see the locus of current flow during the out-of-step condition is a circle. But voltage divided by current equals impedance. Thus, the apparent impedance of the line, as seen by the relays at both ends, will vary during the out-of-step condition. Since the maximum current flow is at 180 degrees, relays at both ends of the line will see this high current as a low impedance, perhaps as a fault. But we may not want the distance relays to trip this line. We may prefer to separate the system at a different location. Why? Well, in this example, generators at each end are feeding a series of loads throughout the system. Suppose the generators at bus 1 become unstable. Say the distance relays trip breakers 1 and 2, isolating the two systems. We now have the generation at 1 with a capacity of 1,600 megawatts feeding its load of 1,100. We have an excess of 500 megawatt generating capacity. The system can support itself. But look at the remaining system. This has a generating capacity of 1,400 megawatts, trying to supply a load demand of 1,900. There is a shortage of 500 megawatts. Ideally, we would have preferred to split the system by opening breakers 3 and 4, so that the two systems would each be reasonably balanced between generation and power demand. In order to achieve this selection, we need to apply out-of-step relays. The out-of-step relay detects the out-of-step condition, and it can then be used to either 1, block the operation of specific relays, or 2, cause tripping at the desired locations. The out-of-step relay operates by measuring the change in impedance as the systems swing in and out of step. We have just seen that the impedance of the line, as seen by the relays, varies according to the changing rotor angle. The out-of-step relay actually measures the effect of this as the rate at which impedance is changing. For example, an out-of-step relay located here at the receiving end bus will consist of 2 zones. The first set at, say, 80%, and the second zone at 110% of the normal line impedance. This RX diagram shows us how the impedance changes as the phase angle changes between the voltage at each end. For example, where the voltages are 60 degrees apart, the impedance seen by the relay is out here. As the generator rotor advances, the angle increases and the apparent impedance decreases. It will first operate the second zone of the relay, and then after a short time interval will operate the first zone. The time interval between the first and second zone operation is important. The relay is set to indicate an out-of-step condition where the time interval is 60 milliseconds or more, since short time intervals, say 5 milliseconds, would probably be caused by a fault on the line. The out-of-step relay at bus S operates to trip its breaker. A similar relay located at the receiving end bus operates to trip the breaker at that end. From the point of view of this receiving end bus, voltage VR is steady, while VS at the other end rotates in a leading counterclockwise direction. At 180 degrees, the voltage profile along the line would look like this. The point of zero or low voltage now oscillates between the far end of the line and the center approximately. Of course, this is the same concept previously discussed regarding the sending end bus. As we have already seen, the out-of-step relay may be used in several ways. That is, 1, to instigate tripping, 2, to block tripping, 3, to block automatic high-speed reclosing. Now, why would we want to block the reclosing action when we have earlier pointed out that fast reclosure actually assists stability? Well, this is true, but once the system has become unstable and the out-of-step conditions exist, then reclosing a line close to a source of generation may well cause a shock to the system that increases the load swings and aggravates the out-of-step conditions. Where the out-of-step relay is used to instigate tripping, the timing of the breaker opening is most important. If the breaker is opened at the precise moment where the two voltages are 180 degrees apart, then an exceedingly high voltage will exist across the breaker contacts, and this could cause breaker damage. For this reason, when the out-of-step relay detects the out-of-step condition, it will delay tripping until the measured impedance starts increasing again. That is, moving through the first zone and out into the second zone again. The impedance increases because the current flow in the line is now decreasing again as the swing continues. At the receiving end, voltage is now beginning to close in on the sending end voltage and so reduce the angular displacement. It's clear that the application of the out-of-step relays varies for each specific condition and location throughout the power system. You should take time to examine the installations in your own power system and work out with your supervisor the rationale for each case. What are the relay settings? What do they do, and why? So we have learned that where out-of-step conditions do exist, the systems must be separated. That each separate system or island will have to be stabilized before the two can be synchronized and reconnected. However, when the systems split into islands, we may run into another problem. That is, one of the islands may have insufficient generating capacity to meet the power demand. In this situation, the frequency will fall and continue to fall until we can restore the balance. That is, power generation equals power demand. If additional generating capacity cannot be brought online rapidly, some of the load will have to be shed in order to restore the frequency to normal. Automatic load shedding is carried out by frequency relays. These are usually installed in distribution substations and are set to disconnect blocks of load at specific frequencies. For example, 59.5 hertz, 59 hertz, 58.5 hertz. Obviously, the load shedding is set up so as to disconnect non-essential loads first. Essential loads, such as hospitals, pumping stations, etc., are not normally included in load shedding schemes. Although it is highly undesirable to disconnect any customers, this is the only manner by which recovery can be achieved. Once the frequencies are normalized, then the power systems can be reconnected and interchange can begin once again. You may well ask, but why can we not operate at a lower frequency, say 58 hertz? Well, the first answer is that certain customer equipment may not function correctly at low frequency. Also, most modern steam turbines cannot operate at low frequency without damaging some of the turbine blades due to vibration. Another more basic problem is that at low frequency, all of the auxiliary plant in the power station will be running at low speed. Consequently, we may not be able to supply sufficient fuel, combustion air, or feed water into the boiler. The output of the generating units would be decreasing at the very time when we need more capacity. Maintenance of the correct operating frequency is essential for stable operation of the system. In this particular tape, we've talked about dynamic operating conditions. We've examined how the system behaves under changing conditions, particularly during disturbances. We have also seen what a vital role protection equipment plays in maintaining system stability and also in initiating the correct action when instability does occur. Incidentally, one way to avoid instability problems on long-distance EHV transmission lines is to install a DC transmission system. With direct current, there is no line reactance, consequently no angular displacement between the DC voltage at each end. But that is another story. Please switch off the tape now and thoroughly review this material in your workbook.